Let's say we have some scientific workload. It has to perform some calculations, hopefully for the betterment of humankind. This workload will need to have some data that it uses, such as arrays, scalars, and matrices for storing intermediate results in. When running, we need somewhere to store the data. Ideally, it should be close to where the calculations are being performed. This is where classic memory hierarchy comes in. As a basic model, we have our processor. We store data in the level 1 cache. This is a tiny, high-speed memory and is close to where the data is processed. However, our size here is limited, typically on the order of a few dozen kilobytes, so we cannot store much data here and generally have to deal with fractions of objects. We have additional levels to the hierarchy, increasing their time to access and decreasing their cost per unit of storage. Since it's hierarchical, if we need to process some data, we must first check if our data is in the L1 cache. If not, we check L2, then L3, and so on, until we find the data, and then bring it to the processor. However, there's another emerging memory model. Often called heterogeneous memory, it disrupts the classic hierarchy by having a variety of memory subsystems that have a mix of properties. For example, reads could be much faster than writes, or we could have cache-like memory that we can explicitly control with software. We could have memory capable of performing some computations, and many more. Without a clear hierarchy, we're then presented with more choices to make. In which memory subsystems do we place our data to get our application to run faster and cheaper? This is where EVOP comes in. Discussed in several papers produced by our host center in the mid-2010s, EVOP adds a number of useful extensions to the Valgrind instrumentation framework. Namely, in software, we simulate a cache and run our workload in this simulation. We collect data about the access patterns of the workload during execution, with a level of detail not possible using hardware counters, and use this data to devise data placement strategies when running in a real heterogeneous memory system. Great, but what's the problem? Well, the original experiments were performed over 5 years ago, and when we run them again, EVOP gives us slight but marked differences about the number of instructions and cache misses for our test workloads. This is a problem, since we want our scientific findings to be reproducible. Thus, it was my job this summer to understand why these results were different, and if possible, reproduce the results from the original paper. First, we want to make sure that we're using the same version of the EVOP code as the original paper. We had access to the Git history of the codebase, and we were able to walk backwards and forwards through different versions of the code. However, Git can be complex, and we discovered that not all of the files in the Git history had been tracked correctly. This meant that the versions of the code from the time of the paper had a mix of files in them, and did not compile. We patched these versions so that they worked as intended, however they still did not reproduce our results. Our next step was looking at the influence of the toolchain versions, such as the flags passed to and version of the compiler, as well as the versions of linked third-party libraries. Exploring the space of tool versions, rebuilding everything, and rerunning experiments repeatedly could become tedious, so we adopted an approach of containerization. With a container, we can describe in a text file all of the tools we need for our application, and the steps used to build and run our experiment. We can then run this container as an isolated environment on a host machine with minimal overhead. Making a copy of the container text file is easy, and using different versions of the toolchain is quick and avoids the risks of doing everything in one system, getting things mixed up. With a large mix of environments, we were still unable to hone in on the original results and found that the impact of the tool versions was minimal. Perhaps there was a perfect mix of compiler options and code versions to get perfect reproduction, but during the project we were unable to achieve them. However, we still have some useful lessons, and results generated by EVOP about our test workloads appear sensible and can be used to inform future work. Now we've established a reproducible workflow, the results today should continue to be reproducible into the future. Regarding the issues with the Git history, we've defined a basic continuous integration system. This will check every new commit to the codebase to see if it compiles properly and optionally passes unit tests. This and the containerization workflow were discussed in other materials I produced during this project. I recommend anyone doing research who wants to start improving the reproducibility of their own work to look at them. In conclusion, I've learned a great deal about low-level instrumentation and the steps we might take in the future to optimize workloads using emerging heterogeneous memory technologies. Though I was unsuccessful in reproducing the original results of the paper, I have taken steps to ensure this won't be a problem in future work, and have produced materials to guide other researchers in making their projects more reproducible. At the time of the original works, these reproducibility techniques were not mature nor common. Today, we are in a better place, but we're still at the early stages of ensuring high levels of reproducibility in HPC research, which is both a technical and cultural challenge. Thank you.